Okay, so we stopped with the protocol stack. So now we can go in depth in the protocol stack of the LTE. So we will start from physical layer, MAC, moving up to in the protocol stack chain. So starting from the physical layer, in the physical layer we have what we define spectrum channel and the spectrum feed. And spectrum is a framework we developed here in CTTC for simulating frequency selective channels. So usually in NS3, most of the radio telecommunication technology relies on a frequency flat channel. So you have just one information for the frequency for the whole bandwidth, which was okay, of course, with the standard FDM or standard transmission techniques. But now with FDMA, which we might have different in frequency, different resource block in frequencies, was not any more reliable. So we developed with this framework. So we will have both in uplink and downlink, two different channels that take care of evaluating the transmission power per resource block basis. Of course, from InnoB perspective, we have the same. The only difference is that here we have different user spectrum fee, because in fact the user can send is a multi-point to point transmission from InnoB perspective. The InnoB receives the information from all the UEs, while from UE perspective we have only one InnoB that is sending us the information. So this is the control plane stack of the UE. Here we have the RRC, the protocols before. As you can see, we have the different barriers. Here is where we manage the actual connectivity for the users. These SRB0 and SRB1 are the standard bearer used for exchanging information for connection, for reconfiguration of the connection. So these are the bearer used for control plane. Here from InnoB side is very similar. The EPC part, so the part of the core, is we have the standard X2 application for the communication between the node Bs when you have an handover, for instance. We have the InnoB RRC for managing the connection to the user, and the EPC InnoB application, which is the application that includes the gateway and the mobility management entity. So this is how they are generated. So as you can see, this is the standard. This is the node that includes the protocol stack from InnoB perspective. So from the antennas, the one of the MME, and the one of the SGW. Of course, these two ones from simulation perspective are in the same node. So let's move to the radio propagation model. So in order to make some reliable measurements on the radio part, we included new models from 3GPP scenarios. So we have path loss model both for indoor and outdoor, counting for external and internal wall losses. The shadowing, according to 3GPP models, is not a 2D shadowing, but it's just a log normal variable. And also a path loss logic that is able to understand whether you are indoor or outdoor and how to evaluate the path loss. We had also a binding model, a simple, let's say, building model, just to consider the standard 3GPP-like scenarios where you have tiers of apartment. We include some antenna models, and for simulating isotropic antenna, like for instance the one of the small cells, where you have or standard Wi-Fi, so isotropic, but also the sectorial one for the big macro antennas. And as I told you before, the fast fading model for pedestrian vehicular scenarios. So from outdoor perspective, the radio propagation model included the Okumurata, the standard one for cellular communication, from 150 megahertz up to 2 gigahertz, and for large distances. Also an empirical model developed by Kuhn for 2.6 gigahertz, the new bandwidth for LTE. For what concerns the short range of communication, the ITU P1411 line of sight, and also the non-line of sight one. So these are usually mostly for short range communication up to 1 kilometer. And we include, as I told you, a building propagation models, a building model for considering indoor communication and also indoor to outdoor communication. Buildings are generated in a very simple fashion. You have just a box and 3 box classes that allows you to define the standard X, Y, and Z coordinates. You can define the number of floors and the number of rooms in order to have a grid of rooms, a matrix, sorry, 3D matrix of room. And the buildings model allows you to install the building in your simulation script. So you have just installed the 3 block class containing the building, position the building in the simulation Scene field, and define the number of rooms and the node condition, whether or not is indoor or outdoor. And then, of course, in this case, when 2 nodes are indoor, we will use this kind of, we'll use this propagation model, the ITU P1238. So that is a model that implements the building-dependent indoor propagation model, including the number of losses, the type of building, and also it considers here, because we consider also outdoor to indoor communication, so the hybrid propagation loss model. In this case, you might have different external losses depending on the walls. These are numbers taken from COST 231. For instance, for when we have a wall of wood, concrete with windows, or stone blocks, as you can see, these are already taken into consideration. The internal wall losses are evaluated assuming that each single wall has a penetration loss of 5 dB, and the logic by itself counts the number of walls. And we use also log normal shadowing as a standard deviation for outdoor to indoor and external walls penetration losses. Well, also this is an aid gain that Ubiquiti suggests us to use in case you have your antenna is on a floor above the ground. You have, it seems from their works that we have such a kind of gain. The hybrid propagation model is in charge of understand where the user are, whether they are indoor or outdoor, whether there is the signal penetrates some walls, and calculate, evaluate according to the fixed loss and the log normal one, what is the actual propagation loss according to the position. This is the antenna model. As I told you, we have the isotropic one. So like, for instance, the standard Wi-Fi router. So we have like this one, this small one. And the sectorial one, like this one, this big one, which is the one typical for a cellular scenario. This, for instance, are an example of a building solution. This is a typical scenario in 3GPP called dual stripe scenario, since we have 2 stripes of apartments, rooms. And this is usually evaluated for testing interference coordination when we have small cells coexisting with macro cells. And while this is a typical outdoor scenario where we have an hexagonal behavior, an hexagonal deployment of the antennas like the one we have typically in deployment. The fading model is an example of what we were discussing before of an integration of MATLAB with an S3. So we provide a MATLAB script in the code, which by using a rel-enchant function can generate some pre-calculated traces. The traces can be configured according to user speed, the number of taps, so the number of different paths that the signal reach. The signal used to reach the destination, the granularity, the frequency granularity, and the length. Of course, depending on the length and the time granularity, the trace is can be bigger or lower in terms of space, I mean. And usually what we do is to maintain this slow and doing a windowing mechanism. So windowing the traces we can use by having a small trace considered to have an infinite fading trace. Of course, this might generate some discontinuities, but in general, it's a common assumption in this case of in network simulation. So the physical model, going more in depth, in LENA only FDD is implemented. There is 2 models in LTE, FDD and TDD. FDD is a frequency division one. We consider, as I told you before, the resource block as granularity. So we have the whole channel. Here is for instance, the typical TTI, so the unit of allocation. We have the resource block that is a group of 12 subcarriers per 11 symbols. So we might have up to 100 resource blocks depending on the configuration of the LTE mode. It goes from 5 resource block up to 100. This is the data part of the physical model, and this is the control part where we have the reference signal, so the controlling signal, what we usually call pilot also, and the control part that defines how these resource blocks are located to user. In uplink part, since the location is already done by the node B, we have directly the resource block from that UE sent to the node B, and also the sounding reference signal, which is the equivalent from UE side for the node B, in order to measure the quality of the signal of the devices, of the user devices. As I told you, for modeling the physical layer, we use the LTE spectrum model. So we have a couple of center frequency and bandwidth that identifies the radio spectrum usage. So we can have the FC define what is called what is the LTE absolute radio frequency channel number, so the central frequency of the LTE. B is the bandwidth, which may be from 1.4 up to 20 megahertz. Support, of course, different frequency and bandwidths according to the standard. And they can be, for instance, as in this case, partially overlapped, totally overlapped, or also but it's not so useful, also completely orthogonal. In this case, UE will automatically use the spectrum model the node B is attached to, so it may change during runtime. For considering the interference in case of overlapping, we adopt the Gaussian interference model. So the power of the inferring signals in linear units are summed up together in order to determine the interference within the resource block. And according to this model, we can evaluate the CQA feedbacks. We have two types of defining the CQA feedbacks. The periodic one that defines CQI is a channel quality indicator. So we can define aperiodic channel quality information for the UE. So we have one information for UE up according to explaining what is the signal strength seen by the user in a scale in 15 discrete values, and also in band CQIs that defines per resource block level, which is the signal quality. In downlink, they can be evaluated either with control channel or data channel when they are available, and in uplink they are evaluated through another time, either by control channel or data channel. The scheduler can filter this information in order to rely only on control feedback or data feedback in order to see, for instance, in order to implement different resource allocation algorithms, for instance. Now we go to the data error model. In this case, since we are talking, as I told you before, since we are talking a network simulator, we consider to use what is called link-to-system mapping technique. So we cannot rely to real transmission chain because it might be too much computational complexity. Actually, there are a couple of examples of people trying to do it in WiMAX and Wi-Fi, and the network simulation was too slow. At the end, they was able just to simulate a couple of links, so it was not actually a network simulator at all. So, but according to this link-to-system technique that has been developed during the WINNER project, and that is adopted also by 3GPP, we can have a very reliable measurements of what is the information on the actual, let's say, performance in a frequency selective channel. So what is the idea is to have adopt the mutual information effective SNR mapping for having the information of the mutual information per resource block basis, combined then and then according to some pre-calculated BLER curves, evaluate what is the transport block error performance. So in this case, we rely on a link level simulator, the Vienna simulator, LTE, based on MATLAB, actually. So this is an example of MATLAB integration with, another example of MATLAB integration with NS3. But of course, this is an offline integration, it's not an online integration, because these curves are pre-charged in the NS3 simulator. So as I told you before, what we do is to generate these curves per modulation and coding scheme basis, because we need to have a specific curve per resource block and per code block in order to have a detailed information of what is the actual code word error rate. So what we do is to decompose the transport block in different code block, look at the modulation encoding scheme, so the order, whether it's a QPSK, 4QPSK or 16QAM, and take the correct graphs and the correct number of code blocks that are generated according to the dimension of the transport block for generating what is the transport block error probability. So this model is adopted for data. For control error, we adopt a different model, which is one based on this evaluation study. This evaluation study carried out in run 4 of 3GPP. So in this case, we rely on evaluating an effective SNR, so a measurement of the signal in a control channel very similar on what we have done in the data. So we evaluate what is the SNR across the whole bandwidth with possible interference in the middle. And with this mutual information, we can extrapolate what is the effective SNR value. And in this case, according to the figures, the control error model figures we have in this technical report, we can decode, we can understand whether the control channel is decoded correctly or not. Of course, in case the control channel is not decoded correctly, we cannot receive all the data, because we don't have the information for decoding the data in this case. And in general, as I told you before, NS3 provides CISO propagation model. So CISO and flat propagation model. In case of LTE, we extended to MIMO solution. So in this case, we extended as MIMO as a gain over CISO solution. This is in order to maintain the computational complexity with a reasonable level, and do not have too much computational complexity and a huge and very large simulation time. So in this case, what we do is to evaluate what is the CINR in a CISO solution and evaluate what are the differences in case of different MIMO solution. So according to the specific MIMO techniques, we might have a positive gain or a negative gain. For instance, in spatial diversity, we will have a positive gain, while with transmission diversity, we will have a positive gain, while with spatial diversity, a negative one. The framework of the WER measurements is based on the framework in which UE has to report the measurement to node B, what they call the measurement that is used for evaluating the power that the user has to use for the node B for transmitting to the user to manage the power control algorithms, and in general for having the bias offset on the power. So these measurements are performed when receiving the reference signal, so the control part. And there are two types of measurement: the receive signal, receive power, so a sort of average power across the resource block. So there's no information on the interference, while in the reference signal received quality, we have an average radio between the power of the cell that I'm attached to respect to the total power received. So these are the two types of measurement, and these are the typical measurement used for both setting the power of the user and also for performing handover, for instance. We also implemented an hybrid RQ model, which is a very important part in LTE transmission chain. In this case, we implemented the soft combining hybrid ER full incremental redundancy. So it's a model in which we consider that each hybrid RQ retransmission provides new information. It's a model that is a synchronous model in downlink, so while it is a synchronous model in uplink. So this implies that in downlink it's a matter of the scheduler to decide whether to retransmit, while in uplink we have a 7 millisecond for retransmitting the original block. The retransmission are mixed with the new one, but of course the retransmission has higher priority respect to the transmission of new packets. And as defined by the standard, we have up to 4 redundancy inversions per hybrid RQ block, which implies that we can transmit 4 new versions of the hybrid RQ, for a new version of the transport block in hybrid RQ for providing more new information and making the decodification chain able to decode the packet. Of course, this has been integrated with our model. So we will not have anymore the standard modulation encoding scheme, where we need to consider a new rate for when we have different code blocks that combine with different redundancy inversion. So from scheduling perspective, we will have, as I told you before, the resource allocation unit is the resource block. The location type is, we use a location type 0, in which resource block are grouped in resource block groups according to this, to this mapping. And we consider the transport block model like in 3GPP structure. So the multiplexing RRC PDU into MAC PDU. In this case, what we have done respect to the other case is that we use virtual MAC headers. So we do not use real bits. So in principle, we were not interested on simulate the overhead of MAC, since it is a sort of overhead that is neglected by the MAC scheduler. So it does not affect the performance from MAC perspective. Since we are just simulating the physical layer, its effect was negligible. This is the adaptive modulation coding scheme adopted by the scheduler. So we have 2 algorithms. One is based on analytical BLER, based on the first version of the simulator. This is a standard formula for obtaining what is the spectral efficiency needed for transmitting a certain data with this SNR. And then we implemented another adaptive modulation scheme based on the Vienna model, so based on the actual BLER curves at the physical layer, as according to what defined in the standard, in order to maintain a 10% of block error rate at the physical layer. So this reflects the standards, while this one is an analytical model based on a theory. Also dynamic tricks mode selection, so the different MIMO modes can be selected according to the information. The interference is present, but actually the scheduler is not using them in this stage. We have not adapted our algorithm for changing the MIMO mode. So now we are in the core of the simulator. So as I told you before, the core is the scheduler, which is based on these APIs defined by the small sign forums. So we implemented all the APIs defined from scheduler perspective. For instance, this is an example of the primitives defined by the scheduler. You will find that these primitives, this underscore, are translated in camel case with camel case typing. And each primitive has its own parameters defined in these structures in the code. So you will have the actual interface like this. This actually is a figure from the Femtoform API. So when you have this kind of parameter, this kind of primitive, you will have this kind of primitive in the simulator passing this kind of parameters. So we'll have a control API for providing information of the cell to the scheduler, of new E, or of generating logical channel, which are the channel used by UE for transmitting and receiving data, and also for releasing the UE. When, for instance, a UE moves from one antenna to another, and so you have to move the user from the node B. This is the scheduling primitive, so as soon as each millisecond, from the physical layer, we receive a trigger that says that you have to schedule the data from a scheduler perspective. So the scheduler receives this kind of information with all the information regarding on the channel state, on the hybrid RQ feedback, and so on, and generates a configuration indication that, according with this configuration indication, the MAC can multiplex the packets from the RRC and generates a MAC packet that has to be transmitted. This is done both in downlink, for downlink, and for the uplink. The LENA supports several scheduler implementations, from the basic one like round robin proportional fair, from a few more complex one like priority set scheduler that allows you also to have some quality of service aware scheduling perspective, especially the last three ones. You can set, for instance, that a user might have a certain bit rate or a certain delay. All the implementation, of course, are based on the FFR API. Well, a few assumption is that these are downlink implementation. In uplink, we implement always the round robin, because we are not interested in right now. We've been not interested right now in of uplink performance, even that there is a few implementation of uplink in the of uplink scheduler, but are not integrated. And also, as I told you before, BLER has a higher priority respect to the transmission of new data. Well, this is the standard round robin. It's very simple. You have just to divide the resource blocks among the active UEs, while in proportional fair, you have to maintain what is the achievable rate, let's say, in a fair fashion among the user. So the user just to be fair according to what they already transmit, the past throughput perceived, window width, which is standard window in system, and the rate they can achieve. So the idea is that we have to maximize this achievable rate per user in order to be fair among all the users. And these are the other schedulers I told you. The maximum throughput are scheduled very simple and used mostly for academic issue, while the token bank are slightly more smart, and the priority scheduler also controls the fairness among users and can target a specific bit rate according to the primitive of the user, the secret period of the user. The MAC layer also implements a random access model. In this case, we have an idle model, so we have not propagation. The random access is a procedure for the user to attach to any node B. So we have just a preamble transmission, so the user can transmit the random access. We detect the collision based on contention resolution. So when we have a reception of two different random access of the same index, we will have a collision. And also the procedure will continue with the random access response, which is another time an ideal message. But the resource consumption are actually modeled by the scheduler. Then the user equipment responds, answer with a message 3. So in this case, we have actual bytes subjected to our model for attaching. And then, in this case, after the node B receives the message 3, the UL is actually attached. So the supported mode are contention based, so for a connection stable, and non-contention based for handover. So it's for setting up a connection mainly. The RRC model, so the algorithm for managing the actual connection per BLER basis, the supported mode are the transparent mode, unacknowledged mode, and acknowledged mode as the 3GPP specs. The transparent mode is a connection without any let's say, overhead. is a simple bypass. The acknowledge mode provides just the sequence number, while the acknowledge mode provides a reliable connection. So it has retransmission and queues for retransmission. The SM mode, called the saturation mode, is a simplified full buffer model used for some testing in when you would like to test the radio performance. Of course, in acknowledge mode, we have segmentation, fragmentation of the packet. The PDUs have the actual headers with real bit, with 3GPP specs, so we can actually spill off the packets and see in Wireshark what is happening. And of course, in case of acknowledge mode, we have the status PDU and the retransmission in case we need to retransmit. What is not supported is the fragmentation of the retransmission PDU. So it supports only one level of fragmentation. The PDCP model is a simplified model for supporting it's moving up the protocol stack. Here we manage different user from the protocol stack perspective. So in another time, in this case, we have also real bytes. We can transfer data both for user and control plane and the status. But we do not support either compression or decompression, so we transmit packets as they are. Of course, the in-sequence delivery is not supported at the PDCP level, only from LRC. The ciphering is not implemented, and also timer-based discard and integrity protection. So what are the standard, let's say, authentication procedure are not supported because we were not interested in evaluating this kind of overhead. So moving up, we have the RRC. In this case, the RRC is in charge of managing the connection of the user. So accept the user, manage their quality of service, performing handovers. So for instance, for system information, so for accepting new user and handover, we implemented the MIB and SIB messages that are the messages in which that the LTE uses for advise the not be. So for providing the information on its channel ID and so on, and for the user for starting the attachment procedure. It works in idle mode self-selection, so the user starts in idle mode and then can attach to a certain node B. It has these states for connection establishment. So when a user has detect a new node B with MIB and SIB messages, can start an RRC connection establishment procedure. And also when we would like to change, for instance, the MIMO configuration or providing some control info, can use this connection and configuration messages. The RRC model accepts the UE measurements functionalities. So we have implemented all the event-based triggering functionality of the events A1 to A5. So A1 to A5 means that when a user goes below a certain threshold or reach a certain threshold and so on, this is in order to plug let's say, to generate your own handover algorithm. By combining different events, you can be less smarter, more smarter. And as assumption, we consider just a one-to-one PCI to EGCI mapping, but this means that the physical channel identity is mapped to only one enhanced global channel identity. This is a LTE terminology, so this implies that we can simulate only let's say, a regional LTE network, but this usually does not affect any simulation. What is important is that we can perform only intra-frequency measurements, so we cannot perform inter-frequency measurements, so user cannot move from one channel to another, where with the channel I mean LTE channel, the one defined by the standard. So you can move from frequency, of course, but within the same channel. In fact, there is no measurement gaps for making they not be able to switch the radio from one channel to the another. So the RRC model architecture, RRC is divided into an RRC logic at the UE side that contains the UE RRC logic. While in ADB, it has an InnoB RRC and a UE manager for managing the RRC logic, and from UE part, the different logic per UE basis. So we have two different types of RRC logic. One is ideal, in which there are no resources consumed. There is actually the message that exchanges through an ideal channel, and the real RRC with actually the real encoding of LTE, so you can use one HARQ for checking what is happening. The ideal one is used usually for testing purposes, specific scenario in which you don't want to have problems on control channel. You would like to have a specific configuration reliable. So this is the state machine. As I told you, from your perspective, you start in idle, and you can do idle search for trying to find an InnoB to be attached. Then when you receive the message, you go to the SIB message, you go to idle campo normally, in which you know that there is a base station. Then you can start the random access procedure for attaching to the InnoB. As soon as you are attached, you are in idle connecting, and then with the RRC connection setup, you go to the standard state that is connected normally. As soon as you might have problem, you return to campo normally with the RRC connection reject. But usually, this is only when in idle connecting, because there's no way, as you're not connected, to become not connected. As I told you, works only on RRC connected mode LTE right now. From InnoB perspective, so we start at the beginning in which we have no context of the user. So we might have a user coming either for handover or for random access procedure. In case of random access procedure, you start the connection setup procedure and you go to connected normally. While in case is a user coming from a new cell, you just perform an handover joining, and with the handover information, you can go directly to the connected mode. Of course, when you are connected, you might need to do an handover. So as soon as you do an handover, you prepare to handover, and when a user left the cells, the context is destroyed. This is a new functionality developed in the Google Summer of Code of 2014, and this is a frequency reuse algorithm. This is algorithm used for managing the frequency when you have among different cells, adjacent cells. The LTE, of course, does not provide any design for this algorithm, but it's quite important to investigate on this. So during this Google Summer of Code, we implement different FFR algorithm for dividing the bandwidth in different way. For instance, one is possible to use the border part for dedicated to the user, but there is very different solutions. The idea is that this part, the FFR algorithm, has to work directly with the InnoB RRC, since it has to know all the measurements from the user side. And from data part, it controls the scheduler in order to tell to the scheduler where to place each user according to its feedback. So these are the standard APIs. So as you can see, which probably are more. This is an example of how it works. So as soon as you have a new information you have to generate a new scheduling information. You have to generate. You have to know which resource block you can use, and according to this map, you have to check whether a user can transmit in a certain specific band. So you can have this frequency use in place, both in the uplink and downlink. There are different frequency reuse implemented. Full frequency reuse, which implies having no frequency reuse. HARD creating different. This is one, for instance, is the HARD dividing the bandwidth between among the three cells. This is the soft, in which we have just according to a certain threshold, we have just that user in the border can have a specific band, or there are many more interesting smart solutions that can adapt according to the threshold of the power seen by the user. Of course, they are very it might be quite difficult to use them, since each algorithm has its own specific configuration, but there is an automatic solution that is recommended to use that avoid problems for configurability. You just configure the 3 types of cells, and the subbands are configured in automatic fashion. The Handover support, so LENA support also Handover, so we have all the API for the algorithm, the measurement configuration, as I explained to you before, coming from the user, and generating events. And these events can generate an Handover in case your specific algorithm of Handover generates an event. For instance, one is A2, A4 RRC, in which if this specific measurement reaches a certain threshold, you have to perform an Handover, or this one, which is the very simple one, which is based on a signal strength. As soon as a certain cell, this implies that simply you attach to the best, with the cell with the best signal. This is an example of how it works. In this case, we have a user moving from inode B to inode 4 in with a linear movement. Start attaching with inode B1 and move attached up to inode B4. So what we have, this is actually is an example in the code. You can generate these graphs in which you can see that the user have this kind of behavior from signal perspective power, and these are the power of the different cells. So when is attached to serving cell 1, here it's attached to serving cell 1, then is detached to serving cell to inode B1. Yes, this is one is D2, and so on. The NAS is the non-NAS stratum. This is a functionality for providing end-to-end connectivity within the LTE framework. So interact with MME for generating, for providing attachment of a node B, for activate the bearer, multiplex the data into a bearer. So differentiate the traffic according to the service you would like to provide. If it's a video application, you might have stringent QoS, for instance, a delay and bit error rate information. So you need to, here is where the BLER are generated according to the requirements for the user. The S1 is the protocol providing you the connectivity, so generating the connectivity from core part perspective. So in this case, we have a real GTU implementation, so we are tunneling the packet within the actual GTPU protocol with GTPU IPv4. So we use a point-to-point link for communicating data, while for control plane we use an abstract model I told you before, that these are just primitives, so in principle system call for setting up new user and new bearer, so new user connection. The X1 is the interface between two inode Bs, so between two antennas. In this case, we have from data plane, we have another time a point-to-point link. So we have a real packet for transmitting data between two inode B. So data, I mean the data of the user. When a user moves to another inode B, the buffer of the user can be moved according to this interface. While for control plane, is just there is another point-to-point link transmitting these packets. In this case, another time are real packets, but they're not. They do not use standard formats, because the standard format implies a very complex coding scheme that we will not be able to. Well, it was very time-consuming to implement it, and we realized it was not so important for the requirements we had for the development of LENA. So in this case, the primitive of the standard handover, request, acknowledge, failure, the status transfer for transferring the data from one base station to another, and for releasing the base station. Also here we have a few primitives for the self-organizing technique. So base station can exchange information on the load and on the resource status update. So they can communicate one to each other for knowing what is the current status. There's 11, so in this case is for creating a session, is the communication between MME and SGW, so for creating session and better, for going out from the LTE network. So is the so we finalized the protocol stack of LTE. So we return back a bit on how to define a simulation configuration. So this is done as usually in S3 with attribute system. The LTE object has several configurable attributes, so we can define it via config file, via command line, or directly in the simulation program. Of course, pre-instance we can pre-configure according either GTK config store, the tool I was talking before for checking the configuration, or simulation, or directly with the simulation program. So the simulation output, LTE generates tons of simulation output. Depends on you on what you would like to do. We start from physical layers, KPIs, so SNR maps, path log matrices, in physical layer, or the transport block traces, so actually how data are transmitted, defining per each transport block, the RRQ level, the modulation encoding scheme, the information about the decodification, all the information about the measurement at the physical layer side, all the trace from MAC layer, and for understanding how the resources are allocated within the simulator, and also going up all the information regarding to the actual connection, so with the IP data, so time averaged stats with, for instance, MAC delay, or RRC delay, RRC queues, till application level. So we can obtain application stat with standard NS3, or by using flow monitor, pickup traces, or and by obtaining this information, you can process it with MATLAB, with another C++ program, or whatever you want. Excel, I don't know. It depends. Actually, this is text traces, so it is flexible to. It's up to you to how to manage it. This is an example, or as I showed before, the 3GPP dual stripe scenario. So we have different. These are small apartments in a 7 cells scenario. So this is obtained with an S3. You can generate this map very easily. There is a simulation script that already creates this scenario. It is in the example. So you can play and decide the number of flights you would like to have, the number of users, the density of the user, the powers, and then you can decide to run a standard simulation or generate this map in order to see what is the status of how you configure the simulation script. So this is generated with Newplot. There is also a Newplot script for moving directly from the text file to the Newplot to this figure. This is an example of the same of before, but moving more in depth in the, let's say, in a single cell. And you can see in this case is a very simple scenario in which we evaluate this SNR by deploying fake nodes. So these are all the points are nodes that pick up the SNR, and then that are attached to the strongest signal. So you cannot do what is interoperator interference with this framework, but definitely it's a good tool for understanding what is the radio environmental map in your simulation scenario. So these are a few hints on the execution time performance. You told before we can move up to 40. In this case, we move up to 40 in OmniNode B. OmniNode B is almost the same, so from computational complexity. You might change that if you have a huge number of UEs. Of course, it might take more time to process, but especially due to memory consumption, because you take more memory, you have larger queues. So this is an example of the execution time performance. As you can see, of course, they increase a lot when the number of inode beings the user decrease due to the fact that the physical layer has to keep track of all the interference among the UEs and the inode bees. So it's an exponential behavior due to the physical layer. And this is the memory consumption. The memory consumption does not test these problems of exponential, because this is mainly due to the fact that you have more, you have to maintain more data for keeping all the structure, the object, using the simulation. So you have this linear, almost linear behavior. So tested, since it was an industrial project, we put a lot of effort in testing. We made some unit tests for specific modules and also system tests for checking whether LTE works properly. Actually, the testing framework of NS3 is an embedded framework in NS3, very powerful, because when you implement a new module, you can directly test whether it works or not. And this is important also when you program in NS3, because when you do some changes and the test does not work anymore, it means that your change probably broken some algorithm or some functionality in NS3. So it is a very powerful tool for both validating in general the implementation of NS3, but also validating your changes in NS3. And the important thing also, the testing framework also covers the Valgrind, the memory errors with Valgrind, which is a tool, very powerful tool for checking the memory errors. NS3 is error-free, memory error-free. So in case you do some strange things with pointer or buffers, so on and so forth, and you have a new Valgrind test, you can easily detect where you forgot to, where you make some changes in a pointer without do something correct, or you are accessing memory in a corrupt fashion. Of course, if you use the smart pointer of NS3, this in principle should not happen. And the build, well, in principle, NS3 is a project that, well, LENA is included in NS3 project. It works in different platforms, so you can either use Ubuntu, Fedora, your preferred one, or even in macOS. So you can use SX for also with NS3 and in general with LENA. And this is not only LENA but also NS3. Each day has been tested according to different platforms. And as soon as we have a different Ubuntu release or OSX release, you have always a problem. And usually this happens when you have a new release on NS3, that sometimes it breaks some rule with GCC compiler with OSX new. So these usually are tested daily, and the developer usually to solve these problems in a rather quick fashion. So it's very reliable from this perspective, especially due to the fact of the open community. So we are currently we are very tight interacting with the NS3 community. Actually, we had the NS3 workshop here the last May. We have the NS3 1-week workshop. So we have the NS3 workshop, the one for presenting paper and works, but also the NS3 consortium the NS3 developer meeting. So the people more involved in the developer for talking about new features and so on. Also the NS3 consortium meeting, because the NS3 is a consortium. NS3 consortium is a collection of the bodies that participates more in depth in NS3, and we are executive member. So, well, we are currently the maintainer of the LTE code, since we are the main developer of the LENA. With LENA, we are the main developer of the LTE. We are continually working on new features. Of course, depending on the project, the effort might be lower or higher. Now we have rather huge effort, I would say. We have the last 2 years we have been a bit slowing down, but now we have quite huge number of projects on NS3, so we are very actively on this. And as I told you before, we are used to participate to Google Summer of Code. So if you are interested on implementing new feature either in NS3 or in LENA, check the NS3 mailing list next spring, usually during March, because you can propose your own project. You will receive a grant from Google Summer of Code, which are quite good money, I would say. And also the people mentoring you will receive some money. And you will have the whole summer for implementing the new feature on NS3, and especially, which is quite interesting, at the end there is also an event, usually in Google facilities in Mountain View, where you students can go, paid by Google. So it's really interesting framework. So here are a few reference papers. There's many more. If you go to this web page, you will find all the information on LENA, the tutorial, some videos, the documentation in PDF, in HTML format, the ongoing activities, and so on. And of course, almost, let's say, all of this information is also in NS3 website. So it's up to you whether you would like to go directly to NS3 or use the CTTC website. So I guess I've been able to.